In this lecture, we will begin our discussion of clinical data standards.
We see from the core content outline that this is a significant part of clinical informatics.
This slide magnifies the details of what we'll cover in this lecture and the one that follows. In this lecture, we'll focus on the first four items here: standards development, history and current process, data standards and data sharing, transaction standards, and mainly focus in this lecture on messaging standards.
This slide shows the key topics that we'll cover throughout this lecture. We'll begin with a discussion of the importance and limitations of standards in clinical information systems. We'll discuss the major types of standards and their roles, including identifier standards, transaction standards, messaging standards, and terminology standards. We'll begin with a discussion of basic concepts of standards and interoperability, and then talk about the four major types. Again, identifier standards, transaction standards, message exchange standards, and terminology standards. Why are standards important in clinical informatics? Well, there's a number of reasons. One is that they promote consistent naming of individuals, events, diagnoses, treatments, and so forth. They also allow better use of data, not only for patient care, but also secondary uses, things such as quality assurance, research, public health, etc. Standards also enhance the ability to transfer data among applications, thus allowing their better integration. And finally, they facilitate interoperability among information systems and users. What actually is a standard? Well, there's a standard for that. It comes from the International Standards Organization, and we'll talk more about standards organizations in a moment. And this has been quoted in the book on health IT standards by Benson. From the ISO definition, a standard document established by consensus and approved by a recognized body that provides for common and repeated use, rules, guidelines, or characteristics for activities or their results aimed at the optimum degree of order in a given context. That is what a standard is. And we also know that standards facilitate interoperability, and therefore we should probably formally define interoperability. One definition of interoperability that's widely cited comes from the IEEE and was published in 1990. They define interoperability as the ability of two or more systems or components to exchange information and to use the information that has been exchanged. This definition was extended for healthcare by a now defunct organization called the National Association for Health Information Technology, and this statement was endorsed by 40 other major healthcare organizations. Interoperability in health IT was defined as the ability of different information technology systems and software applications to communicate, to exchange data accurately, effectively, and consistently, and to use the information that has been exchanged. The IEEE has updated its definition of interoperability and now defines it as the ability of a system or a product to work with other systems or products without special effort on the part of the customer. Interoperability is made possible by the implementation of standards. It can be helpful to define levels of interoperability, and this framework shown on this slide has been used in other contexts outside of healthcare. Sometimes the numbers are different, but we can review the levels to understand the different levels of interoperability. Level 1 is no interoperability, things like snail mail, fax, telephone, etc. The next level up is machine transportable information, sometimes called structural interoperability. The information that's exchanged cannot be manipulated. It's something like a scanned document, an image, or a PDF file. The next level up is machine organizable, or sometimes called syntactic interoperability, where the sender and the receiver understand the vocabulary. So things like email or files that might be in proprietary format. Finally, the next level is machine interpretable interoperability, sometimes called semantic interoperability. And here there are structured messages with standardized and coded data. So for example, when there are coded results within structured notes, or laboratory results, a structured and coded with a standard terminology system problem list and so forth, represent semantic interoperability. There are many examples of standards throughout human history that have demonstrated value. Back to the time of Roman chariots, for example, where the wheels of the chariots were a specified distance apart so that the Romans could move around on their chariots in their cities. A more recent vintage of that is railroad tracks, which once the standard distance between each track was defined, enabled railroad cars to be interoperable on different railroad tracks. Telephones have standards that enable us to call around the world. ASCII text in computers, so the pure text in computers, there's actually some minor differences between Windows, Macintosh, and Unix, but for the most part, ASCII text on one computer can be displayed in another. Wi-Fi is another standard throughout the world now, enabling us to connect computers, smartphones, tablets, other devices wirelessly to the internet. And global financial transactions that enable us to use our bank cards with different banks in other countries and so forth. And I'm sure you can think of additional examples. There are both benefits and limitations of standards. Obviously, the benefits are what we've already discussed: interoperability, and also allowing innovation to take place on a common standardized foundation. There are, however, limitations of standards. There may come to be dominance by one segment of the industry. They may end up stifling innovation because we can't innovate beyond the boundaries of the standard. In reality, standards are usually a mixed bag. For example, Microsoft has evolved a number of standards: the Windows operating system, the Office productivity software suite, Word documents, Excel documents, etc. Another example of standards not achieving success is the language of Esperanto, which was meant to be a common language that would be used especially in science and business. Esperanto obviously did not succeed, and in fact English prevailed in this function for becoming essentially the common human language by which science and business is conducted. Another issue with standards is that in many areas there are multiple standards from which to choose, and this leads to a quote from Tannenbaum, a computer scientist, although some argue that others have said this. But in any case, the quote is that the nice thing about standards is that there are so many to choose from, which, of course, having multiple standards undermines the importance of standardization. There are different approaches to developing standards. Described by Ed Hammond, there are 4 major ways by which standards emerge. One is ad hoc, where various groups who have an interest in a standard agree to informal specifications. There are also de facto standards, where a single vendor controls the industry. and something like the Microsoft Office format is an example of that. Standards may come about from a government mandate, where a government agency creates or adopts a standard and then mandates its use. And then finally, there's the consensus process that most would agree is probably the best approach, where interested parties work together in some sort of open process. Most of the standards development in healthcare have come from the consensus approach, and the article by Marshall overviews the processes and the organizations involved in healthcare that lead standards efforts. Another nice overview of standards comes from a document authored by Keith Boone called Health IT Standards 101. Boone is a prolific blogger about health IT standards. Hammond describes the stages of development of standards, beginning with an identification of the problem, a conceptualization of the solution, discussion among the stakeholders, eventually emerging a specification for the standard, then an early implementation so it can be tested and adopted. Eventually, there is conformance of systems to the standard, and then finally certification so that those who adhere to the standard are certified in doing so. There is an alphabet soup of standards bodies. Most of them are private nonprofit organizations. This slide lists the major standards bodies in the U.S. The American National Standards Institute, or ANSI, is the U.S. organization that accredits standards development organizations, or SDOs, including those in healthcare, and some of the SDOs that ANSI has accredited in healthcare include the Accredited Standards Committee, or ASC X12. Another one is Health Level 7, which we'll talk about extensively. And then there's the American Society for Testing and Materials, or ASTM, which itself has a Committee E31 on healthcare informatics. There are also international standards bodies, and the main one is the International Organization for Standardization, or ISO, as its acronym is pronounced. ISO has a technical committee 215 that focuses on health informatics standards. There's also a European standard organization, the European Committee for Standardization, or CEN, as its acronym from the French is pronounced. And CEN has a technical committee 251 that focuses on health informatics standards. And then finally, there's the International Telecommunication Union, or ITU. This is a UN agency that is focused on telecommunication standards in general, not limited to medical technologies.
There have been a number of standards leadership efforts by the U.S. government over the years. A very early one was the Consolidated Health Informatics Initiative, the first attempt to adopt standards that were ready for use by health-related U.S. government agencies. This was followed by the Healthcare Information Technology Standards Panel, or HITSP, one of the early efforts of the Office of the National Coordinator for Health IT, or ONC. And this was an effort to identify standards that were ready for use and also look at gaps that needed to be filled in standards. After the passage of the HITECH Act, ONC formed the Health IT Standards Committee, which continued work in overseeing and recommending standards. And all standards activities now have been folded into a single Health IT Advisory Committee that ONC maintains. ONC has also had help from other federal agencies. The National Institute for Standards and Technology, or NIST, focuses on standards in general and has devoted some effort to supporting ONC in these efforts. The National Library of Medicine has also helped, focusing on ensuring that terminology standards support various messaging standards in health IT. There have been a number of standards activities at ONC that have guided the process. A major event was in 2014 when an organization called JASON, which is a federal scientific advisory committee, called for moving to more modern application programming interface or API approaches to interoperability. ONC then established the JASON task force to respond to these recommendations and develop evolving plans and documents to chart a path forward. This led to the implementation of the Argonaut project, which explicitly developed plans to implement standards and achieve interoperability. ONC also created an interoperability vision for what it hoped to accomplish with standards and a roadmap on how to get there. Part of that roadmap involves a standards advisory, which is a catalog that's updated annually of standards that are ready for use in operational systems.
Another important standards-related organization in healthcare is Integrating the Health Enterprise, or IHE. This is a non-federal effort, and it attempts to identify and demonstrate solutions to real-world interoperability problems. This is usually done through organizing of interoperability showcases that demonstrate these solutions in action. IHE has various clinical and operational domains, and then each of these domains produces technical framework documents, often in coordination with other domains. Ultimately, these are published, resulting in a trial implementation of the solution, and then, if successful, the profile will be published in final form. Here's an example IHE profile coming from the domain of patient care coordination, and there are specific activities that take place within this domain that have functionality related to patient care coordination. We can't have a complete discussion of standards without mentioning the HIPAA legislation. And in fact, health information standards were a key focus of the Health Insurance Portability and Accountability Act of 1996, which at the time was also known as the Kennedy-Kassebaum Bill. The major focus of HIPAA legislation was actually health insurance issues. There were efforts to reduce denial of insurance based on pre-existing conditions and improve portability of health insurance across jobs. Of course, that part of HIPAA is largely forgotten, and what we remember now are the standards, mostly the standards around privacy and security, but there were other standards specified in HIPAA as well. In particular, standards for financial transactions and code sets. There were requirements for unique identifiers for patients, healthcare providers, and employers, although we'll see that the patient identifier part never came to be. And then finally, this development of privacy and security standards, which is essentially what HIPAA refers to now when we use that word. In the rest of this lecture now, we'll take a tour through the major clinical informatics standards, again in 4 categories: identifiers, transactions, message exchange, and terminology. There are standards or proposed standards for the different participants in healthcare, and we'll discuss identifiers for patients, providers, employers, and health plans. Let's start with discussion of patient identifiers. There are clearly benefits and risks to identifiers that specify an individual patient. One of the benefits, of course, is the easy linkage of records. So if there's a global standard identifier, we can link together records from different healthcare settings and encounters. This in turn facilitates health information exchange, and it reduces errors and costs that arise from duplicate records. What are the risks of patient identifiers? Well, same as the benefit, easy linkage of records, which of course can potentially compromise privacy and confidentiality of individuals. The problems of duplicate and overlaid records are not trivial. They cost money, and the longer that it takes to identify and correct the error, the more expensive it becomes. Those who have duplicate records are more likely to have missed abnormal test results. And the figure on this slide shows the difference between duplicate records, where there is one individual in multiple records, and overlaid records, where there are multiple individuals connected to a single record. If we are going to have patient identifiers, there are certain attributes of them which were laid out in a report by Connecting for Health. Patient identifiers should be unique, so there's only one person for a given identifier. A patient identifier should be non-disclosing, so the identifier itself, the code, should disclose no personal information. It should be permanent, so that it's never reused. It should be ubiquitous, so everyone who participates in healthcare has one. It should be canonical for an individual, so each person has only one, and it should be invariable or not change over time. Clearly, one solution for patient identifiers with the characteristics described on the previous slide would be to have a government-issued patient identifier, and many countries do this, especially industrialized countries. New Zealand has a national health index, and it has a nice website that describes why there should be a national health index, why it's important, how patients' privacy is protected, and so forth. The country of Iceland also has a national identifier and has devoted a lot of effort to genotyping its population, thus creating a national genetic database. In Singapore, there's an identifier that's actually not limited to healthcare. There is a national registration identity card for all citizens, and then for all long-term visitors, there's a foreign identification number, and these are used as identifiers in healthcare. And most other Western European countries use government-issued patient identifiers without much controversy. But in the United States, we don't have government-issued patient identifiers, despite their being mandated by the original HIPAA legislation, but public pressure forced postponement and eventual abandonment of the requirement for patient identifiers within HIPAA. Some have argued that perhaps we should use the Social Security number as a national health identifier. The problems with the Social Security number are both technical. They don't adhere to the attributes that we saw a moment ago from Connecting for Health. There are many duplicates. Social Security numbers are reused, and there's no check digit that allows checksum validation. And of course, Social Security numbers are used for many other purposes and have been shown to help in re-identification of data from public sources. Some have argued we should have a voluntary approach. This has really never caught on, but there has been the development of a standard for this approach. Many argue that a national health identifier in the U.S. is not only unnecessary, but also politically infeasible, especially given the high level of distrust of the federal government. The Connecting for Health report outlined a potential approach, but others concluded that it was not worth the political fight to fight for a national health identifier. And it's also been argued that there may be other ways to achieve the goals of national identifiers, such as linkage of records through various data fields. Another concern about national patient identifiers is that it's a fairly expensive undertaking for a country of more than 300 million people. There are a lot of expenses up front, and the benefits would only accrue later. However, there are still those who advocate a unique patient identifier and argue that it would reduce errors and improve information system interoperability in the US. Again, the cost would be substantial, anywhere from $3.9 to $9.2 billion, but offset by other improvements in the healthcare system. And many advocates of this argue that it would not significantly increase the risk for security breaches over the other options that we use for linking records. So what is the alternative to a national identifier? Well, there are many researchers who have developed probabilistic matching algorithms that link patient records, and their level of accuracy is quite high, but there are still problems in that many data elements are non-standardized, or sometimes called dirty data, and of course there is missing data. One approach that's been advocated is to create a globally unique identifier by having a local master patient index plus a holding institution, something akin to an email address where there's a record at a given hospital. This identifier could be unique, permanent, non-disclosing, and ubiquitous, and allow then records to be linked more easily with probabilistic matching algorithms. Once in place, such a system could lead to the development of a record locator system that would achieve the linkage, and the other requirements for this sort of approach would be security, authentication, data linkage, and of course global participation of the entire population. A recent report from ONC assessed the current state of patient record matching, and it advocated that this was an imperative to address problems of patient safety, care coordination, and data quality. This report noted that the current state-of-the-art works well, but would benefit from standardization of patient identifying attributes in the record that would facilitate linkage. So, for example, names, suffixes, date of birth in a standardized format, current and historical addresses, phone numbers, and gender. These would all facilitate data linkage, and then there would need to be a process, of course, for handling changes in any of these data elements across the healthcare system. This report advocated further research to evaluate various linkage algorithms and additional attributes that might be used to facilitate linkage, and the report also advocated the wide dissemination of best practices. Much less controversial than patient identifiers are provider identifiers. The US used to have the Universal Physician Identifier Number, or UPIN, and this was maintained by the government for physicians who treated Medicare patients. Of course, not all physicians treat Medicare patients, especially, for example, pediatricians. And so a new system was developed called the National Provider Identifier, or NPI, and this is assigned to all U.S. physicians through the National Provider System, which is overseen by the Department of Health and Human Services. It's a 10-digit number with the last digit serving as a check digit, and in fact, CMS will no longer process healthcare claims without use of an NPI. There are also standards for employers and health plans. Employers have a National Standard Employer Identifier, or EIN, and health plans have a health plan identifier and an other entity identifier. These are mandated by the Affordable Care Act. That concludes our discussion on identifier standards, and the second type of standard is transaction standards, and the transaction standards for healthcare in the United States are the ASC X12N standards, and these were mandated in the HIPAA legislation to encourage electronic commerce for health claims, and at the time simplifying the situation of several hundred different formats for health claims. HIPAA mandated the use of these for healthcare business electronic data exchange under the guise of administrative simplification. The original version of the ASC X12 standards were called 4010, and then in 2012, these were superseded by the 5010 standards. This slide lists some of the 5010 standards, things like health claims and equivalent encounter information, enrolling, disenrolling in a plan, eligibility, payments, claim status, coordination of benefits, and so forth. These ASC X12 standards seem pretty mundane and probably straightforward, but it turns out that one of them is very important, played an important role in the problems with the original healthcare.gov website. And one of the reasons for the healthcare.gov website not functioning when it was first launched was that health plans had not properly implemented the 834 standard for enrollment and disenrollment in health plans. And in fact, there were many other lessons about software engineering, IT procurement, and other aspects of large IT projects that can be learned from the healthcare.gov story. Let's turn our attention to the third category of standards, which are message exchange standards, and we'll cover the message exchange standards that are listed on this slide, starting with HL7, followed by DICOM, standards for devices, e-prescribing, labs, patient summaries, and health IT platforms. Probably the most important messaging standard, indeed maybe the most important standard in all of healthcare, is HL7. HL7 is both a standard but also an organization. And the full name of the organization is HL7 International, or Health Level 7 International. And HL7 is the organization that develops the major messaging standards for healthcare. The name HL7 comes from the OSI 7-layer model of computer network communications. Now, when we say HL7, we may be referring to HL7 version 2 that is widely used, and it is a syntactic-oriented standard. But there is a newer version of HL7 that's completely different from version 2 called version 3, and it's much less widely adopted, and it aims for semantic interoperability. One of the challenges of HL7 is that the documentation is less than ideal. One can find voluminous standards documents on the HL7 website, but they are not very easy to read to get an understanding of how HL7 works. There are some overview books by Benson and Trotter. HL7 version 2, as noted in the previous slide, is supported by most vendors. It's widely used. And it's mostly a syntax where the sender and receiver must understand the meaning of the messages. However, in later versions of version 2, there has been the addition of more and more semantics or meaning so that the identifiers start to take on commonly accepted meaning. HL7 version 2, as we'll see in the next slide, is implemented by bar-delimited ASCII text files, and each message has segments that consist of a 3-character identifier and then values that follow after it. So we'll see examples of the message header, the event type, the patient identifier, and the results header and details. Here's an example of an HL7 version 2 message. It happens to be in version 2.5, and this example comes from the Benson book, which shows the HL7 message on the left and its essentially English translation on the right. So this is a report from a lab about a test that took place on a certain date. There's a patient who has a date of birth and an address. The message concerns the results of a swab of the right foot that was done at a certain location in the hospital by a certain physician. The swab grew out a particular type of organism, Staphylococcal aureus, and it has varying susceptibility to different antibiotics. Here's another HL7 version 2.5 example. If you look closely at this, you can figure out that it is a report of an electrocardiogram, and the findings on the electrocardiogram are a ventricular rate that is lower than the atrial rate. And of course, we see this in atrial fibrillation, which is what is the diagnosis on the EKG. As noted a few slides back, the subsequent releases of HL7 version 2 have added particular semantics. So again, whereas version 2.1, the first implemented version, was very basic, version 2.3, for example, added scheduling and finance, and then 2.3.1, pathology and allergies. Version 2.5 added data items related to U.S. meaningful use regulatory requirements. Version 6 started to change the data types, whereas previously a coded element was now either coded with the exceptions or coded with no exceptions, meaning that the element needed to adhere to a specific code standard. Version 2.7 added collaborative care, some additional lab orders and results, and version 8, 2.8, added authorization and ordering information. One of the limitations of HL7 version 2 is that it's a syntactic standard, so there is no standard for what actually goes in the messages. The sender and the receiver need to use the same language to process the message. HL7 version 3 is an attempt to introduce semantics or meaning into messaging so that there is a common language across all of healthcare and that any sender and any receiver can communicate in HL7 version 3 if they adhere to the standard. This, of course, is semantic interoperability. The foundation of HL7 version 3 is something called the Reference Information Model, or RIM. It's an object models of entities that pass messages between them, and it's implemented in extensible markup language, or XML. Many people believe HL7 version 3 to be very complicated, perhaps overly so, and some have gone further in their criticisms of it, such as Barry Smith, who's the best known and most articulate of the critics of HL7 version 3. But let's try to get an understanding of how HL7 version 3 works. Again, everything is based on the RIM, which uses an object-oriented approach that defines healthcare interactions based on 5 abstract classes. The first is the entity, so these are different things in the world: people, organizations, other living subjects, drugs, devices. Some entities have roles, so for example, a patient and a practitioner. And there's participation in those roles. So there's a performer of a role, there's the target of a role. There is then an act that takes place, and the act has clinical or administrative definitions, such as an observation, a diagnosis, a procedure performed, and then there's an act relationship, the act of diagnosis. From the RIM, essentially all clinical, administrative, financial and other activities of healthcare can be expressed, and this is done by putting constraints on the classes and what comprises them. So here's an example of an HL7 version 3 message for a pulse that's measured at a physician office. And you can see it's quite complicated, but there is a patient and a doctor and an observation, which is a pulse rate. And of course, the observation needs to be modeled, and it's typically done in the entity attribute value or EAV format. And ideally, there would be some sort of standard terminology, for example, a rate of 50 beats per minute. One of the most important recent developments in messaging standards is the emergence of the Fast Health Interoperability Resources, or FHIR. In some ways, FHIR is moving backwards, but in other ways moving forwards. In response to the complexity of HL7 version 3, FHIR steps back from the complete semantic interoperability that version 3 adds, although it is expressible and makes use of the RIM and clinical document architecture. But it moves forward in developing an API that is commonly used in modern internet standards. Having this API allows different systems to communicate with each other, particularly over networks. There's a basic building block of FHIR called a resource, and a resource has a common way to define and represent its data elements, building them from simpler data types that define common reusable patterns of elements. There's then a common set of metadata that describes the data in these resources, and then there's a human readable part so humans know exactly what the data mean. One challenge for all standards, especially new ones such as FHIR, is that the documentation can be overwhelming. However, FHIR has developed a relatively short web page that describes FHIR for clinical users and uses the analogy of a file cabinet. So the API can search through folders, it can read a particular one, it can create a new folder, it can update a folder, it can delete a folder. It also provides a history of changes to the folder or the entire system, and also has the ability for transactions so that a bunch of folders can be acted on all at once.
This slide shows a current list of resources available in FHIR from the FHIR website. This list will continue to grow over time, and the hope is that it will cover a large proportion of medicine and standardize how these various entities are described so that better interoperability can be attained.
This slide from the FHIR documentation shows a couple resources, in particular for patients and medications. As I mentioned earlier, HL7 is not only a messaging standard, but is also an organization, and the HL7 organization has a number of additional activities. I'll mention a few here, but there are actually many, many more. The first additional activity I'll mention is the Clinical Context Object Workgroup, or CCOW, as its acronym is pronounced. And the goal of CCOW is to manage the context of caregivers who may need to access different computer applications in the process of care. The goal of CCOW is to achieve an often stated goal in healthcare, which is single sign-on across applications, networks, accessing data, and so forth. CCOW defines a protocol that enables applications to link or understand the context of the patient, the provider, the encounter, and so forth. CCOW is not itself widely used, although an implementation of it has been described, and other approaches to single sign-on that don't use CCOW have also been developed. Another important effort within HL7 is the Clinical Decision Support Work Group. The overall goal of this group is to reconcile the various competing approaches to clinical decision support and clinical guidelines. Because of these different approaches, it can be difficult to move clinical decision support that has been developed in one system to another. There are projects within this work group. One is the virtual medical record, which is a data model that represents input and output to clinical decision support systems. There's also a terminology model. There's a formalism for data manipulation by clinical decision support. There are also projects around developing formal methods for process and workflow, as well as taxonomy of services or actions that get evoked by clinical guidelines. Another major project of the HL7 organization is the Clinical Document Architecture, or CDA. CDA came about from the recognition that a good deal of healthcare information exists in documents, which are usually read by human readers. But if there were ways to structure these documents, we could potentially make them computable and pull out structured data. What CDA does then is define an XML-based standard structure and metadata for clinical documents. Within these documents are templates. These can be reusable and computable. Or there can be unstructured documents, the typical document that's all text, and that can be wrapped in a CDA framework. The current release of CDA is version 2, and there are 3 levels of CDA. The first is the general specification of the document. The second level is the definition of document types and then the allowable structures within those types of documents. And then the third level is when we actually completely structure the data within the document and express this data in the RIM. Here's another way to look at CDA documents, and this comes from Health Story, which is an effort that advocates the structuring of CDA documents where it's cost effective. So most documents come across as narrative text, and at least at this point, it's cost prohibitive to do more with them, but that's the first level. The second level is to begin to structure the documents with the reusable templates described in the previous slide, and then ultimately that third level of having coded discrete data elements. An example here shows SNOMED CT concepts elaborated out within the CDA document. And then the purpose of all of this structuring of documents is to allow functionalities such as quality reporting, decision support, clinical applications, and meaningful use. This notion of reusable templates has been elaborated further, and we now call this approach consolidated CDA. And the approach to consolidated CDA is that we have document templates for the common types of documents that we use in healthcare. We'll see examples of this in a moment, but things like history and physical reports, operative reports, progress notes, discharge summaries, and so forth. Within those document templates are sections, and these sections can be standardized, and then the sections have actual data, and those are called entry templates. We see an example here of different types of documents that are based on different sections with specific types of data. Consolidated CDA was part of the stage 2 of meaningful use, and the implementation guide for consolidated CDA defined 9 document templates. There are obviously more types of documents in healthcare, but these 9 were deemed to be the most important. The continuity of care document, which we'll describe more in a moment, but other documents that are more common to medical records historically, like consultation notes, discharge summaries, history and physical, operative note, progress note, etc. These 9 document templates can be made up of the section templates, and 60 have been defined, and then within those section templates are data entry templates, of which there have been 82. So for example, on the right-hand side, we see the continuity of care document and the templates that go into it. We also see the history and physical exam, and we see there are some section templates that are also in the continuity of care document. And again, these section templates are standardized, as is the data within them, and we therefore have templates that make up CDA documents, and so sometimes this is referred to as templated CDA. The next messaging standard we'll look at is the Digital Imaging and Communications, or DICOM standard. DICOM was developed by the American College of Radiology and the National Electrical Manufacturers Association, and it's mainly a messaging standard around images. DICOM defines how images and their associated data are moved between electronic devices, including information systems. DICOM is used in most picture and archiving systems, or PACS, that are used in hospitals for managing radiology and its images. One of the challenges that we face in the modern era is that images come from a variety of sources, including digital cameras and cell phones, and there's a growing challenge of how to move those images into electronic health record systems, particularly when DICOM is not used. This slide shows a depiction of a DICOM message. The format has a header and then the image proper. The header contains a variety of metadata. It includes information about the structure of the image, the modality, the software format of the image, such as JPEG, if there's compression, how much compression there is, and so forth. And then after the header comes the image itself. Another group of standards is used for medical devices. And before we talk about those standards, it might be valuable to define what exactly is a medical device. The U.S. Food and Drug Administration, from the U.S. Food, Drug, and Cosmetic Act, defines a medical device as listed here: an instrument, apparatus, implement, machine, contrivance, implant, in vitro reagent, or other similar related article that is intended for the use of diagnosis or management of disease, and is intended to affect the structure and function of a living organism. One early effort to standardize data from medical devices was a project called the Medical Information Bus. The goal was to develop standards to control and to link information from medical devices. Most implementations of the Medical Information Bus just transfer data between devices, but the standard itself has the capability to issue commands, and as such, one could, for example, remotely change the settings of an intravenous fluid pump. The Medical Information Bus became the IEEE 1073 standard, and then was superseded by an international standard of ISO 11073.
There are some more recent medical device standards. One comes from a project really called the Open Source Integrated Clinical Environment, or OpenICE. This is a prototype clinical ecosystem that allows medical devices to be connected and used in clinical applications. Part of this environment includes the Medical Device Plug and Play Interoperability Program, which aims to allow devices to be plugged in and to work automatically, somewhat akin to how we plug USB devices into computers and they connect to the computer and interact seamlessly. Another effort is the Continua Health Alliance. This is a consortium of companies and organizations that are focused mainly on the interoperability of personal telehealth devices.
This slide shows the personal health ecosystem that the Continua standards are focused on. We have a variety of sensors in the personal health ecosystem, everything from scales and blood pressure cuffs and glucometers and devices that administer medications. The data from those devices connects in a variety of ways to computing systems. The connectivity may be Bluetooth, it may be Wi-Fi, USB, direct Ethernet combination, and so forth. The data then gets aggregated on computational devices, everything from computers to cell phones to set-top boxes, and then it's passed across the network to services such as electronic health records, personal health records, disease management systems, and so forth. The next standard we'll talk about concerns electronic prescribing. The National Council for Prescription Drug Programs, or NCPDP, has developed a family of standards for pharmacy claim benefits, one of which is SCRIPT, and this is the standard for electronic communications between a prescriber and a pharmacy. The meaningful use criteria require the NCPDP and SCRIPT standards for electronic prescribing. Another standard concerns reporting of laboratory results. This is the EHR Laboratory Interoperability and Connectivity Standard, or ELINCS. The goal here is to standardize laboratory ordering from clinicians and then reporting back to their EHRs. This standard actually uses HL7 version 2, and it constrains the ORU field of HL7 version 2 to define a set of allowable elements. The ELINCS standard is maintained by HL7. Another important functionality for which a standard would be useful is a basic document or snapshot that describes the patient's current state of their care. This led to the development of the Continuity of Care Record, or CCR, which was described as a set of basic patient information consisting of the most relevant and timely facts about a patient's condition. The goal was that when a patient was either referred, transferred, or discharged among different healthcare providers or facilities, that this document would contain basic information allowing the provision of continuity of care. The original Continuity of Care Record, or CCR, however, was not compatible with any existing standard, so HL7 and the vendors took the CCR standard and implemented essentially the same functionality in something that was compatible with existing standards, namely HL7 version 3 and, more importantly, the clinical document architecture. This gave rise to the Continuity of Care document, or CCD. The CCD now provides a way to create a patient summary to move among different healthcare providers and organizations. However, all is not perfect in the implementation of the standard. There are errors that arise. There's also allowable variation from the standard, and that has limited its goal for semantic interoperability, but CCD is still an important standard that can provide a summary of a patient when they move from one setting to another. The ONC further defined a required data set for the CCD that would be required for meaningful use stage 2. The data elements listed here are the required data set for the CCD in meaningful use stage 2. Another messaging standard is the Blue Button Initiative, which is, quote, a public-private partnership to empower consumers with easy and secure access to their health records from a variety of sources in a format they can use. The Blue Button Initiative began with the Veterans Administration, which provided a blue button on their website that allowed patients to download an electronic summary of their medical data. This was widely received and lauded, and that led ONC to launch the Blue Button Toolkit to help facilitate development of Blue Button functionality for other EHR and personal health record systems.
One of the criticisms of modern EHR systems is that they're large, monolithic software systems. Mandel actually calls them traps and argues instead what we need is platforms that can build and innovate on top of these platforms that in essence function like an operating system. This led to the development of the Substitutable Medical Apps Reusable Technologies, or SMART project. It was one of the 4 research centers funded under the HITECH Act by ONC. The idea behind SMART is that we develop apps, and the apps can be smartphone apps or web apps or even software applications running on a regular computer. And these apps then can access the underlying store of information. They can read the information, they can write it back and interact with it. SMART really took off when it paired itself with FHIR, and so we now have SMART on FHIR that uses FHIR as that API to read and write data. There has been much innovation with SMART on FHIR. It's been used for genomics and precision medicine applications, and most of the major EHR vendors have supported some aspect of SMART on FHIR, and innovators can begin to implement apps using the SMART on FHIR process on top of commercial EHRs, the large traps that Mandel originally referred to. Let's perform some interaction here. On this slide, I will present 3 situations and ask for the best messaging standards, and the answers are on the next slides. You should try to answer here before you move on to the next slide. So first, what is the best messaging standard for a patient summary when a patient is transferred from a hospital to a skilled nursing facility? Next, what if we wish to transfer laboratory data from a hospital to an emergency department in a health information exchange? And finally, what is the best standard if we want to transfer a previously performed imaging study in a freestanding radiology center to a healthcare setting? The answers to these questions is first, the patient summary for transfer from hospital's skilled nursing facility is done best with a continuity of care document, or CCD. When laboratory data is being transmitted almost between any type of system, but certainly in a health information exchange, HL7 version 2 is the best messaging standard. And finally, a transfer of a imaging study, again, almost no matter where the transfer takes place, the most likely standard to be used is DICOM. For further reading, probably the best sources are first the chapter by Hammond et al. In the short-lived textbook that gives an overview of standards, and a more recent book that goes into much more detail and also introduces FHIR is the book by Benson and Grieve, Principles of Health Interoperability, 3rd edition.